Let's look at a few examples, a few applications of simple harmonic motion. Okay, just a reminder, harmonic motion refers to or deals with displacement of an object that moves in we can say a sinusoidal pattern, motion. That just means that we could model the motion, the distance, the displacement that it travels over time using a sine or cosine graph. And so again, our sort of general equations were d for displacement is equal to a for the amplitude sine of omega t, or we could use d equals a cosine of omega t. And again, the d is for displacement, t is time, a is amplitude, and the omega is just related to the period. Okay, in the graphs that we were looking at before, just replace omega with k. All right, it's the same stuff. Okay, so in this example, this first example, we have an object that's moving in simple harmonic motion, and it has an amplitude of 35 centimeters and a period of 8 seconds. And we want to we're assuming that the displacement at t equals 0 is at its maximum. We want to write an equation that models the object's motion. Okay, so we already know from what we're told in the problem, we know the amplitude is 35. So we know A is 35 centimeters, and we're told the period is 8 seconds. Okay, that's the information that we're pulling off of the problem. Okay, the rest of the problem where it tells me the displacement at t equals 0 is at the maximum, that information is used to determine whether we're talking about sine or cosine. Sine starts at the midline and it goes up, down, and back to the midline, right? Whereas cosine starts at the maximum and goes down and back up to the maximum. Okay, so which of these situations are we given in this problem? Are we starting at the midline, sort of at the equilibrium, or maybe that point of rest, or are we starting at a maximum? Well, we're told that we are starting at a maximum. Okay, so we're actually going to use the cosine in this example, okay, because of the information that we're given. Okay, so to write my formula, we know d is equal to the amplitude, which is 35 centimeters. We'll just put in the 35. We are using cosine because it starts at the maximum. We need to find omega, though. So how do we find omega? Remember, omega and k, from what we looked at with our graphs earlier, omega is the same thing as k. And so k, we computed k using 2 pi over the period. Okay, so to find k, we're going to say k is 2 pi over the period, which is 8 seconds. And so k is going to be pi over 4. So we're going to have 35 cosine of pi over 4t. Okay, so that is the function, that's the equation that describes the displacement over time as a function of time. If the amplitude is 35, it starts at its maximum, and it has a period of 8 seconds. All right, let's try another one here. It'll be very similar. We have an object, again, is moving in simple harmonic motion. This time we are told the amplitude is 1.2 meters. And this time we're given a frequency, so not the period, we're given the frequency of 0.5 hertz. And we're going to assume the displacement at t equals 0 is 0. So 0 meters. So that means it's not the maximum or the minimum, it's at the midline, it's in the middle. We want to write the equation that models this displacement as a function of time. Okay, so we are told the amplitude is 1.2 meters and the frequency is 0.5 hertz. Now, a hertz is really per second. Okay, so it's how excuse me, it's how many periods do we have per second. And so to find the period, we know that the period and the frequency are reciprocals of each other. So the period is going to be 1 over the frequency, and the frequency is a half. So 1 over a half, 1 over 0.5, and 1 divided by 0.5 is going to be 2. So the period is 2 when the frequency is a half, and we know the amplitude is 1.2. So we know all the pieces that we need. We still need to find omega, don't we? So how do we find omega? Omega was 2 pi over the period, so the 2 pi over 2. And so the omega is going to be just pi. So now we know everything that we need to write our equation. We're told that its initial displacement at t equals 0 is 0 meters. So that means we're going to deal with the sine equation. So the displacement d is equal to 1.2 sine of pi t. Okay, so that is the function that describes a harmonic motion where an amplitude is 1.2 meters. The period is 2 seconds because the omega value is pi, and it's sine because we're starting at the middle. We're starting at 0. All right, let's try a couple other examples here. Now, suppose these will be hopefully maybe a little bit more application oriented here. Suppose we have a common smoke detector, and it produces a sound wave that can be modeled by the function s of t equals 65 sine of 1040 pi t, where s is the sound wave's displacement over time t measured in seconds. We want to determine the amplitude, the period, and the frequency of the sound wave. Okay, so again, our function that we're given is s of t is equal to 65 sine of 1040 pi times t. So if we look at our general formula, that was d is equal to a sine of omega t. So in this case, the a has to be that 65, and omega has to be 1040 pi. It's the value in front of the t. So what is the amplitude? So in this case, the amplitude is 65. Okay, I don't have units for that in this case, but our amplitude would be 65. So the sound wave, as the wave travels through time, it has a displacement of 65 from instead of just being at a 1. Okay. What is the period? So again, the period is 2 pi over omega. So it's going to be 2 pi over 1040 pi. The pi's cancel, and so we're left with 2 over 1040. We could reduce that. We could also just go ahead and divide that on the calculator. So 2 divided by 1040 is going to be a really small number. It's going to be 0.0019. And in terms of our function here, because it's just defined in terms of seconds, this is in seconds here. So the length of period, the length of one period of this sound wave is 0.0019 seconds. So it's a very, very short wave, but which usually sound waves, light waves do have kind of short waves. How do we find frequency? Well, remember, frequency and period are reciprocals of each other. So it's 1 over the period. And so in this case, it would be 1 over that 0.0019. You could also think of it as 1040 divided by 2. And that means our frequency is 520. So what's the reciprocal of seconds? It would be 1 over seconds. And 1 over seconds is actually hertz. So the frequency is 520 hertz. It has a period length of 0.0019 seconds, and the amplitude, the sort of the strength of the sound wave is 65. All right, let's do one more here. Say we have a large clock tower that's being constructed so that the center of the clock is 120 feet above ground. The minute hand is supposed to be 8 feet long, and it's going to have a light located at the tip of that minute hand. We want to write a function that models the height of that light that's on the tip of the minute hand. We want to write a function that models the height of the light over time t measured in minutes, and we're going to start when midnight corresponds to t equals 0. Okay. I'm a visual person, so I like to see kind of what I'm talking about here. So let's draw a picture. So we have a clock tower here, right? We have a clock on it, and we're told that the center of this clock needs to be 120 feet above ground. Okay. And we know that the minute hand is 8 feet long. So if the minute hand was pointing straight up, that means that the minute hand, the tip of the minute hand where that light's going to be, is going to be 128 feet, because I know it's 8 feet long. And if the minute hand was pointing straight down, it's going to be 8 feet lower. So that would be at 112 feet, right? Because it's 120 up to the middle, and then 8 feet above that would be 128, and 8 feet lower would be at 112. So that gives me, if we think about sort of our sine and cosine graphs, that would translate to a midline at 120, and then the maximum would be 128, and the midline, or the minimum, sorry, would be 112. Okay, so when we think about our sine or cosine graph, that's what we're looking at. We are also told that midnight corresponds to t equals 0. When a clock strikes midnight, where's the minute hand? It's pointing straight up, right? So at t equals 0, so when we're on the y-axis, we are going to be, the minute hand is pointing straight up, so that light is going to be at the top of the graph. And as the minute hand then goes around, it's going to curve down until it hits the bottom. So when does it point straight down? After 30 minutes. And then when's it going to go back up? After 60 minutes. So the graph is going to, we're going to have a graph here that cycles every 60 minutes. And that should make sense, right? Because we're talking about the minute hand on a clock. So what's the period? The period is 60 minutes. Okay. And if it's the period, we could find our k value, or we could think of it, since we're going to do harmonic, we could think of it as omega. Omega is 2 pi over the period, so 2 pi over 60, and 2 pi divided by 60 reduces a little bit to pi over 30. All right, so we know the omega value, and we need to find our amplitude, which again is not too hard to get here. The amplitude is the distance from the midline to the top, or from the midline to the bottom. And so in this case, from 120 up to 128, that tells me my amplitude is a distance of 8 feet. Okay? And so we're almost done here. To write the equation, so for part A, to write the equation, we could say that the height of the light is going to equal our amplitude, which is 8 feet. Is this graph sine or cosine? If it starts at the top, curves down, goes back up to the top, that is actually cosine. And we know omega is pi over 30, so pi over 30t. All right. There's just one extra little piece that we need here. So we didn't see this in the previous examples, but this graph is not centered at the x-axis. Its midline is 120. So it has been shifted upwards a distance of 120 feet. And so to account for that in our formula, we need to add 120 at the outside at the end of our equation. So my function for the height of this light that's on the tip of the minute hand is going to be h equals 8 times the cosine of the quantity pi over 30 times t plus 120. Okay, so that's how that function there models the height of that light over time. And just kind of a second part to this, how high is the light at 12:40 a.m.? So for that second part there, remember 12 midnight is t equals 0, so 12:40 would correspond to a time value of 40 minutes. So I want to take 40 minutes and plug it in for t. So h is going to be 8 times the cosine of pi over 30 times t, but I'm going to put a 40 in for the t, and then we have plus 120. Okay, so this is going to be 8 times the cosine. You could write this as 40 pi over 30, but the tens, the zeros are going to cancel, so we're just going to be left with 4 pi over 3, and then plus 120. So we're going to have 8 times the cosine of 4 pi over 3. So we can go ahead and use our unit circle values here. Cosine of pi over 3 would be a half. 4 pi over 3 is actually in the third quadrant on our unit circle. So cosine in the third quadrant is negative. So this is going to be a negative 1/2. And so we have 8 times the negative 1/2 plus 120. 8 times the negative half is a negative 4. So negative 4 plus 120. So our height after 40 minutes is actually going to be at 116 feet. So hopefully there's just a few examples illustrating how simple harmonic works, how we can write the functions. We just need the amplitude and either the period or the frequency. And then we need to know whether it's sine or cosine, which again, sine or cosine just depends on where the graph starts. Does it start at the midline or does it start at the maximum?